All right, section 3.4, we are going to start using that whole synthetic division process. We start with our rational zero theorem to help us find possible rational zeros. And then we are going to look at using that synthetic process to narrow down that list and actually find all the zeros. Okay? So that's how far we're going to get today. Quick review. How do we divide with long division? I'm going to pause the recording. I want you guys to divide this out quick. All right, so 7 goes into 266. How do we do this? 7 goes into 26. How many times? 3. We put a 3 on top. 3 times 7 is 21. And then we subtract, we get 5. And then we bring down our 6. 7 goes into 56. 8 times. 8 times 7 is 56, which means we have no remainder. Yes? And anytime we end up dividing and having a remainder of 0, it means we found some factors. When there's no remainder, this is telling us that 7 and 38 are both factors of 266. That's going to be really important today, getting that remainder of 0. All right, that's how we prove that we have factors or zeros of our polynomial. Then it says use SD. SD stands for synthetic division. Use synthetic division to show that x minus 2 and x plus 3 are factors of this polynomial. Our goal is to have no remainder. Okay? If they are truly factors, we should have remainder 0. Okay? So it says your goal is to get a 0 for the remainder. So, what if I said factor 72? Okay? What's one factor of 72? 2. You could divide out a 2 and we get 36. Then could we start breaking the 36 down? Does that make sense? So when we think about doing factors, we could do a factor tree, right? And we could just keep breaking things down. We can do the same thing synthetically. We can take this big polynomial, which is an x to the 4th, a quartic polynomial, and we can just keep narrowing it down. Okay? I refer to this as stacking. So we don't have to start over every time. Like we didn't have to start over with 72 to find more factors. Okay? If x minus 2 is a factor of it, that means when we divide synthetically, we should have no remainder. How do we divide x minus 2 out synthetically? We put a 2 in front. Okay. We need the coefficients from our polynomial. Are we missing any terms where we need to worry about a 0? No. Okay. So our coefficients are 2, 7, negative 4, negative 27, and negative 18. Okay? So synthetically, we're going to show that this 2 should work. We start by bringing down our first 2, and then we multiply. 2 times 2 is 4, and we add our column. 7 plus 4 would be 11. Multiplying again, 2 times 11 is 22. Adding that with our negative 4 is 18. 2 times 18 is 36. Adding that with a negative 27 gives us 9. And 2 times 9 is 18. Adding with a negative 18 would be 0. So, did we just show that it's a factor? Yes, because the remainder is 0. Now, we're going to drop that off. I don't want you to completely cross it off or erase it. I just want you to put a slash through it. Okay? There's no remainder. What we have left, the 2, 11, 18, 9, that row is my new smaller polynomial. Right? The 9 would be my constant, the 18 would be my x's, the 11 would be x squareds, the 2 would be x cubes. So I've now moved from an x to the 4th polynomial down to an x cubed. Okay? I can keep going. Now I'm trying to show that x plus 3 is a factor. So what am I going to do with this smaller polynomial? Okay, so we just drop that 0 remainder out of there. And we just go to the 9. And what am I going to put in front? and negative 3. Okay? We bring down our 2 to get started and multiply. We add our column. We multiply negative 3 and 5. Adding our column gets me a 3. Multiply negative 3 times 3 would be negative 9. And adding, we have no remainder again. Okay? So, have we done what they asked us to do? Have we shown that those two are factors? Yes. Now, what is left? On my last row here, a 2, 5, and 3. What does that mean? Good. So we have one factor was x minus 2. We proved that worked. One factor is x plus 3. And what we have left now is a quadratic, right? 2x squared plus 5x plus 3. So, using synthetic takes our x to the fourth down to a quadratic. We could try factoring this. We could do quadratic formula, right? We have methods to solve quadratics, all right? So your goal is always to use enough synthetic division to get it down to a quadratic. And then you have options, okay? All right. So the process we're going to go through uses something called the rational root theorem. It says if we have a polynomial, we can find possible rational roots. And I want you to underline that. Possible rational. We are just making a list of options. It doesn't mean they're all going to work. Okay? But it's a starting point. Rational numbers are numbers that can be written as fractions, as ratios. So any fractions or any decimals that are repeating or ending, terminating, would be considered rational numbers. Okay? Irrational numbers would be things like the square root of 2. All right? Those are numbers that are decimals that don't terminate and don't repeat. We might have zeros that are irrational. We might have zeros that are imaginary. What this list is doing is it's telling me if there are any rational zeros, it's going to help me find them. And hopefully that gives me enough information that I can find the other ones with quadratic formula or completing the square. Okay? So, how we find them? We take factors of our constant term. And in this example here, C is my constant, yes? So we want factors of that constant, and then we're going to divide by factors of the leading coefficient. So we basically need to use our first and last numbers and list all the factors of them. What that's going to do is it's going to give me a whole list of all these possible rational numbers that might work. Okay? All right. So our first step, we are going to figure out how many zeros are we looking for. Okay? It's called the fundamental theorem of algebra. Basically, it tells you that the degree of your polynomial tells you how many zeros there should be. So if I'm dealing in this first example with an x to the fourth, then I have to have 4 zeros. Okay? It doesn't mean they're all going to be real. It doesn't mean they're all going to be nice rational numbers. But I am going to have to find 4 of them. Our next step is to make that list. Okay? If you want to abbreviate that, just list possible rationals. All right? List our possible rational zeros. So based on this example, I need factors of my constant term divided by factors of my leading coefficient. What's my leading coefficient? 1. It's always beautiful when your leading coefficient is 1 because dividing by 1 isn't going to do anything, right? It's going to make this pretty simple. So we can have positive or negative factors. We're going to simplify it just by putting that plus minus in the front of the whole list instead of in front of each individual number. I need factors of 8. What are numbers that multiply to be 8? 1, 2, 4, and 8. And we're dividing by factors of 1. Okay? So I actually have 8 possible rational zeros. I have 1, 2, 4, and 8, and I have -1, -2, -4, -8. So there's 8 possible ones out there, but we know we are only going to find a maximum of 4 of them. Okay? Our next step is to narrow down that list. We don't want to try all 8 synthetically. So we're going to use the calculator to help us narrow down our list. So what I need you to do is grab your calculators and type that equation in your y equals screen and look at a graph of it. Okay? All right, so we have x to the 4th minus x cubed plus 2x squared minus 4x minus 8. All right. Zoom 6, remember, will reset your window to a standard window very quickly. All right. So what are we seeing? How many places does it cross the x-axis? 2. All right. Remember, zeros and x-intercepts are the same thing. Right? So I'm looking for where it's hitting the x-axis. Where does it look like it's hitting? At what values? -1 and a +2. All right. Now, we said there were supposed to be 4 zeros, right? But if I go back here and look at my equation, an x to the 4th graph should have both arrows pointing up, correct? So if I have that picture from my graph that looked like this, there's no way I can turn around, right, and try to hit the x-axis again, because then my arrows are pointing down. So from this picture and the equation, I'm assuming there are 2 nice real answers that I saw in my calculator, and the other 2 are going to be imaginary. Okay? So what did the graph suggest? Was it -1 and +2, or the other way around? -1, +2? Okay. Then our next step, we have to prove that. Because just because the calculator looks like it's hitting at -1, it could be hitting at -0.95. All right? We have to show that they actually work. And by pulling out those 2 zeros synthetically, we are going to take this x to the 4th polynomial down to an x squared. Okay? And then our last step will be to take that remaining polynomial and find those zeros. We can use the quadratic formula. We can use completing the square. We have options. All right, so my prove step. All right, verify or prove. So basically, we do list, we do graph suggests, and then we prove it. Okay? It doesn't matter which order you try the zeros. If we do have any fraction zeros, I would suggest doing those last because our polynomial is going to get smaller as we go. So we'll have less to work with. My coefficients are 1. Help me out. Is that a -1? 2, -4, -8? Okay. I'm going to go ahead and start with the -1. And my goal is to have 0 here, right? We don't want a remainder. If -1 is truly a 0, I should have 0 remainder. All right, go through our synthetic process. Does it work? Okay. Now, we are going to stack this synthetic division. So instead of going back to the whole first row of numbers again, I can drop off that remainder and just keep going with this smaller cubic polynomial. Okay? Now I'm going to try the 2. Multiply add, multiply, add, multiply, and add. And again, it gave me no remainder. So I have shown, I've verified that -1 and +2 are zeros. But we have to find all of them, okay? Even if they are imaginary, we have to find them. Even if they're irrational, we have to find them. So we have to look at what we have left over. This piece right here. Put your x's back in. What would we have? We'd have an x squared, no x's, and a 4. How do we find the zeros of that? Subtract the 4 over, good. Square root both sides. X equals plus minus the square root of -4. What's the square root of -4? 2i. So we end up with plus minus 2i. Okay, so final answer. My zeros are -1 and +2. I proved those synthetically. And I found the other two, the 2i and the -2i, using factoring and square rooting. Okay? So we were looking for 4 zeros, and we found 4 zeros. All right. We're going to go through a couple of these because what happens after we get through the synthetic process is a little different on each one. Okay? So for this one, to make our list, we need factors of our constant, so factors of this 4, 1, 2, and 4, divided by factors of the front 4, another 1, 2, and 4. So we're going to go through all the different fractions we can create with those numbers. All right, so I'm going to start with the top one and divide by each of the bottom numbers. So 1 divided by 1, 1 divided by 2, and 1 divided by 4. Okay, then I'm going to go to the 2 on top and divide by each of the bottom numbers. 2 divided by 1 is 2. 2 divided by 2, and I already have that on my list, so I don't need to write it again. 2 divided by 4, and I have that. Now move to the 4. 4 divided by 1. 4 divided by 2 is on my list. 4 divided by 4 is on my list. So I actually have 10 possible rational zeros. 5 positives and 5 negatives. Okay? Now, go to your graph. Enter your equation. All right, look at our graph. This is a very typical x to the 4th graph. It looks like a W. Where does it look like it's hitting? A 2 and a -2. What else? You can always trace it and narrow that down. You could change your window. Let's say my window is changed from a -3 to a 3. We'll stretch that out a little bit. Can you tell now? Half and -1/2? Are those fractions on my list? Yes? Okay, so our graph is suggesting a -2 and a +2, a -1/2 and a +1/2. If it's not on my list, I'm not even going to look for it. I'm not going to try it. Okay, that's why we make the list. It has to be on there to try it. Now we go to prove it. We have 4 zeros that we're looking for, and we saw 4 on our calculator. So we might be able to just synthetically do all of these. Okay. I'm going to start with the whole number ones, the integer ones, and save the fractions for later when it gets smaller. So I'll start with the -2. I am missing some terms. So my coefficients here need to be a 4, 0 for my cubes, negative 17, 0 for the x's, and 4 for the constant. Okay? All right, so we're going to stack this. Bring down our 4, multiply, add, multiply, and add. Multiply the negative 2 and negative 1, add our column, and one more time. So do we get no remainder? All right, drop the 0 off and work with the rest of the coefficients. Okay, this time I'm going to go with the 2. Repeat our process. So multiplying and adding, multiplying and adding, multiplying and adding. And that worked as well. Okay. Now I have to try the fractions. But notice that I only have 3 numbers to work with, right? So that's why we saved our fractions till the end. The polynomial keeps getting smaller. So I'm going to bring down the 4, multiplying. Negative 1/2 times 4 would be negative 2. Adding. Multiplying negative 1/2 times negative 2 would be positive 1. And again, I get 0 remainder. And my last one, I'm going to try the positive 1/2. 1/2 times 4 is 2. And that worked as well. Okay? Now, the 4 that's left here at the bottom, that is a constant, right? No remainder, the 4 would be a constant. So that's a 4 that basically has been factored out like a GCF that's been pulled out, okay? My zeros are positive and negative 2, positive and negative 1/2. I have found all 4 and I've proved them all synthetically, okay? Now, you do have another option. Once we did 2 synthetically, we took our x to the 4th and we got it down to an x squared right here. Okay? That is 4x squared, no x's, and a minus 1. Yes? Could we have found the zeros from that? We could have added the 1, divided the 4, and then square rooted. It would give us the 1/2 and negative 1/2. We could factor it. And find our zeros that way. Okay, so you do have some options. As soon as you get it down to a quadratic, you have other routes you can go. If you want to keep doing it synthetically, that's fine too. All right. What is the problem with this next one? There's no constant. We go to make our list, we look for our constant, we don't have one. Okay? Could we factor an x out of everything? We would have an x squared plus 6x minus 2. And if we're trying to find the zeros of that, we know this first one. All right? We know one of my answers is going to be just a 0. The other one, x squared plus 6x minus 2. I could go through that process, right? I could make my list, I could check the calculator, I could try synthetically to find them. Is it factorable? So we have this quadratic. It's not factorable. Again, I can go through that whole list process, but if they're imaginary or irrational, I'm not going to get any help from my calculator. What are our other methods for solving quadratics? What'd you say? Quadratic formula, right? Quadratic formula will always work. What's the other one that will always work? Completing the square. Okay? Both of those methods will always get you your solutions. Whether they're irrational, imaginary, it doesn't matter. So, I'm going to go through this one and use completing the square, just as a quick review for you on that technique. It doesn't matter to me if you use quadratic formula or completing the square, but for this one, I'd like you to try the completing the square. Okay? When we complete the square, we move our constant to the other side. So I'm going to add the 2 over to the other side. And then we have to complete the trinomial, right? We have to make it a perfect square trinomial. To do that, we're looking for that missing number that we're going to add to both sides. I take half of my b term. In this case, b is a 6. Half of 6 is 3, and then I square it, right? Half of b squared. So squaring a 3 gets me a 9. I'm going to add a 9 to both sides. Remember, whatever you add to one side, you have to add to the other. All right? The left side now is a perfect square trinomial that will factor into 2 identical things. What does it factor down into? Good. On the other side, 2 plus 9 would be 11. To solve for x, I need to get rid of that square, so I'm going to square root both sides. And then I'm going to subtract the 3 over. Now, I am getting 2 solutions, correct? Negative 3 plus root 11 and negative 3 minus root 11. Those are not imaginary. There's no I in there. That means if I looked at my calculator, I would see it crossing. It's just that those are decimal numbers, right? They're not nice rational numbers. Okay? So my zeros here are 0 and negative 3 plus minus root 11. How many is that? 3. Is that what I was supposed to find? Okay. All right. Our last one. We do have a constant on this one, so let's go ahead and make our list. We need factors of 34 divided by factors of 1. What are my factors of 34? Plus and minus 1 times 34 and 2 times 17. I'm dividing by factors of 1, which would just be 1. All right, let's look at our graph. All right, our equation. X cubed plus 10x squared plus 33x plus 34. All right, I'm going to do zoom 6, put it back to a normal window. What are we seeing? We're seeing a negative 2. It's a pretty typical cubic looking graph, right? It looks like it's crossing the x-axis at negative 2. Is negative 2 one of the numbers on my list? Yes? Okay. So we're going to use a negative 2. We're going to prove that and see where that gets us. All right. My coefficients are 1, 10, 33, and 34. We go through our synthetic process. All right, and it does work. What we have left now is x squared plus 8x plus 17, correct? Is that factorable? Okay, so we need to solve it using another method. We do have a middle term, so we can't simply square root both sides. So quadratic formula or completing the square are your 2 options. Okay? I'm going to work through it completing the square. But again, you guys know the quadratic formula. You can use that as well. I'm going to bring the 17 to the other side. What is my missing number? So half of 8 would be 4. Squared would be 16. I'm going to add 16 to both sides. My left side factors My right side gets me a -1. What are the factors? Good. X plus 4 squared. All right. Square rooting both sides. What's the square root of -1? I. All right. And then subtract our 4 over. Okay. So we found one real solution. All right. It was a -2. The other ones are imaginary, -4 plus minus I. Now, I chose to complete the square in the last two examples, and I did that because my first term was a 1, and my middle number here was even, right? So it's easy to cut it in half and square it. If you did not have a 1 as your A value, or you didn't have a nice even number for B, then I'd go to the quadratic formula. It's just faster. Okay? So your assignment is page 386. You are going to do 17 through 24. All right? I need to see all the work just like I've shown in the examples here.